So if take a look at the first fundamental theorem of calculus, which is the definite integral, we're going to look at the second fundamental theorem. So go ahead and make a tab. I'm going to title it in a later video actually. So title second fundamental theorem of calculus, which basically says that if f is continuous on an open interval containing a, some constant a, then for every x in the open interval, the listening check, underline the word continuous. Underline continuous. The derivative of the antiderivative, which is taking the derivative of basically the integration of a regular function, is equal to the regular function with respect to x, even though it's the integration of a function with respect to t. Right, so it's going to sound a little confusing right now, but when we do an example, we'll see that it's really, really, really easy. So basically, when you take the derivative of the antiderivative of x with respect to x, it's going to give you back the original function with respect to x. This is a listening check. Color in antiderivative. Color in antiderivative. Alright, so an example, if you take the derivative of the integral from some constant 4 to a variable x of the function 10 over this radical t with respect to dt, I'm going to do the long one, then I'm going to show you what the second fundamental theorem says. So let's rewrite this function with that t with the exponent. So the derivative of the integral from 4 to x of 10 to the t to the negative 1/2 dt. So it just bring in the power. So let's go ahead and integrate it because that's what it's closest to. So if we integrate that, we add 1 to the top and divide it by whatever we get. So that's what we're going to get. And then if we go ahead and simplify that, we're going to get 20 t to the power of 1/2 or 20 radical t. Using the first fundamental theorem of calculus, you're going to plug in the first variable, the top thing first, subtracted by the bottom thing into the equation. Alright, go ahead and evaluate that or simplify that. So you're going to get the derivative of 20 radical x minus square root of 4 is 2 times 20 is 40. Alright, so now we have the derivative of that. Well, let's rewrite this in power again so that we can take the derivative really easy. So that's going to be 20 to the x to the power of 1/2 minus 40. Taking the derivative of that, you bring the half down, subtract 1 from it, so you're going to get 10x to the negative 1/2. And that can be rewritten as 10 over radical x. So after you take the function, you integrate, then differentiate it, this is what you get. So I'm just rewriting that down. Well, the second fundamental theorem of calculus has a shorter way of doing this. And it basically says, again, f has to be continuous on the open interval, but it basically says that you take that top variable, you plug it in to whatever your function is with it, where the variable is, and you just ignore everything else. So if you plug in x where you see the t, you'll get the answer we just got, which is 10 radical x. So integral has to be going from a constant to a variable, and all you do is you plug in that top variable into the variable in your function, and that's your answer. That's what the second fundamental theorem of calculus is. So what it does is saves you all of this work. So I didn't need to do all of that work because it's just that simple. So let's take a look at a few more examples. So taking the derivative of the integral from 1 to x of cosine t dt. And again, the fundamental theorem says if it goes from a constant to a variable, right, all you do is take that variable on top and you plug it into the function where you see the variable in the function. So you just replace it. So it's cosine x. That's it. That's the answer. And if you do it the long way, you can verify it, of course. Let's take a look at another example. This is a listening check. Color in example 3. Example 3. Once again, it goes from a constant to a variable. So all you do is you take the variable and you plug it into the function where you see the variable in that function and write it down. So that's x squared minus 1. And that's it. To the power of 20. That's it. Alright, let's take a look at one more example where it can be a little bit tricky. We're going to look at one where it doesn't go from a constant to a function, a constant to a variable. It actually goes the other way around, from a variable to a constant. But it's really, really, really simple. When that happens, all you do is rewrite it. So it doesn't go from a constant to a variable, it goes from a variable to a constant. All you have to do is rewrite it. So that can be rewritten as the derivative with respect to dx of the constant to the function. But because I've done that, I switched the order. I just have to put a negative outside. That's all I do. That's the only difference. And that becomes like everything else. So all I have to do is switch the order and make it negative. Okay, once I have that, again, it's now constant to a function, to a variable. You put the variable into the function everywhere you see the variable. So now that's going to be negative, and then cosine x squared plus x. And that's pretty much it. Okay, so the second fundamental theorem of calculus saves you a lot of time. All right, let's practice.